This presentation is about analysis of a frequency symplectic phenomenon in wireless power transfer for intelligent application. First, we will read the presentation part, which is about introduction, wireless power transfer principle, frequency symplectic phenomenon, Complex coefficient, and mutual inductance, design and simulate basic of wireless power transfer system, results, conclusion, and references. First, we will talk about wireless power transfer, which is considered now as an important technology in recent years, especially the magnetic resonance coupling techniques, which is called MRC. Wireless power transfer, as said before, is important and great technologies because of many advantages that have, like reliability, safety, no need wires, and so on. However, there are many factors or parameters can affect on the system performance of wireless power transfer. One of these parameters is called complex factor, which is variation in it tend to make a splitting in frequency of the system. This is called of frequency splitting phenomenon, and later we will talk about this frequency splitting phenomenon in details. This figure shows typical block diagram of wireless power transfer, which consists of about DC power supply, DC to AC inverter, and the transmitter coil, which is this three part is a transmitter side of wireless power transfer system. The receiver side consists of receiver coil, AC to DC rectifier, and load, which is uh, maybe smartphones or electric car or any device. Wireless power transfer principle. I will explain this principle of work on figure 2 to be more clearly the principle of work. First, when an AC current is flow through the transmitter coil, which is this, and a magnetic flux is delivered. The receiver coil, which is this, is then getting this flux and is changed over into an AC voltage across it. This is a simple explain for how the wireless power transfer works. Now we will talk about the frequency splitting phenomenon, which is considered an important characteristic in magnetic resonance coupled wireless power transfer. But before we will explain the frequency splitting phenomenon, how it's occurred, we should know there are three situations of coupling in wireless power transfer, which is overcoupled, critical coupled, and undercoupled level. Where the best situation of these three situations is the critical coupled level, because the amplitude of a frequency has one peak and maximum power transmitter efficiency become high at the resonance frequency. Also, the receiver side has a higher power than the other two situations, which is over or undercoupled levels. Now we will explain how the frequency splitting phenomenon occurs or why it's occurs. When the distance between the two separate coils decrease, the coupling factor increases due to the function between the distance and coupling factor. So, as the distance decreases, K is or coupling factor increase, and which tend to be a frequency splitting phenomenon if the coupling factor become above the critical coupled of the coupling factor. This tend to make a maximum power transmitter efficiency achieved at two new frequency points that will be above and below of the resonance frequency. So the condition of the frequency splitting phenomenon to occur is at coupling factor become above the critical coupled factor, and later in the result we will show or know how is the frequency splitting phenomenon occurs clearly. Here, a simple schematic diagram system has been designed and simulated in ADS program, as shown in figure 3. Three different frequencies, 10, 20, and 30 MHz, with varied coupling coefficient has been simulated. to show the effect of coupling factor on system performance at each frequency. At 10 MHz, we can see that at coupling factor equal to critical coupled 0.04, the maximum power transmitter efficiency become at 10 MHz, which is equal 98%, where at K equal 0.05 over coupled level, at the maximum power transmitter efficiency decreased sharply at the resonance frequency and become maximum at two new frequencies, which is above and below the resonant frequencies at 9.8 and 10.3 MHz. Here at 20 MHz, we can see at coupling factor equal 0.09 critical coupled level, maximum power transmitter efficiency is become also at 20 MHz because the K equal 0.09 is a critical couple and the maximum power transmitter efficiency is equal 98%, where at K equal 0.03, which is over coupled level because the maximum power transmitter efficiency is decreased sharply at 20 MHz, which is a resonant frequency, and become higher, or we can say maximum power transmitter efficiency at two new frequencies above and below the resonant frequency, which is at 19.78 and 20.84 MHz. Here at 30 MHz, we can see at coupling factor equal 0.01, which is a critical coupled level, the maximum power transmitter efficiency also become at the resonant frequency and at equal 90%, where at K equal 0.09 is maximum power transmitter efficiency decrease sharply at resonant frequency, which is called this over coupled level, and the maximum power transmitter become higher at two new sided frequency, as we said, with 29.86 and 30.5 MHz. This is shown the difference between the critical and overcoupled level. From the conclusion here, we can see table 1 frequency split comparison at three frequencies. At 10 MHz, the frequency splitting phenomenon occurs at coupling factor equal 0.05, and at 10 MHz, the frequency splitting phenomenon occurs at coupling equal 0.03, and finally at 30 MHz, the frequency splitting phenomenon occurs at K equal 0.02. From this table, we see that, or show that the table shows that as the frequency increase, the probability of frequency splitting phenomena at lower coupling factor increase. This is because the function between quality factor and the frequency, whereas at higher frequency, neglecting the effective of small resistance tend to high quality factor, and that result in coupling factor decrease. Also, coupling factor variation is affected on power transmitter efficiency because coupling factor is a function of distance. As the coupling factor increase, the distance decrease, and vice versa. So this is the final of the presentation. This is some of the reference, and thank you for watching and listening.